Welcome back to Management Decision Tools. In this section, we will look at LP examples and we'll sort of flip our screen a little bit to uh, see how we do it in Excel also. So there are two parts to it. When we give a problem like this, so here's an example, when we have this M&D chemicals showing us this business problem. And we're trying to mimic realism here. So in real life, we might be having a tour in M&D Chemicals company compound. We might be interviewing the management to, collect data and understand what are they manufacturing. Oh, they're doing two products, right? So it'll be some sort of a real life field work to gather the data, to know that their total productions must be at least 350 gallons, and we verify that with a couple of employees and all that. So in real life, it'll be hard work. So to save us those hassle that might deviate our attention on the actual translation skill, we'll just lay out the business problem here in text. So all the data gathered, they are right, they are correct, they are not having ambiguity, and they are recorded accurately. There's no loss in information and everything. So major customers order for 125 gallons of product A must be met. What does that mean? Uh, let's look at this and see how we might come up with an idea of an LP formulation. After scanning through, there are parts where they give us numbers and all. It says the objective is to minimize total production cost, right? All right, good. Find a production schedule. So we know the objective function. Objective function is to minimize some sort of expression, linear expression involving total production cost, because that's the variable we are watching to try to reduce. And what are the how many and how much, right? Remember, those give rise to decision variables. The hint is given by production schedule, right? What's a schedule? Schedule refers to uh, who, what, where, when, how. Yeah, so who produces product A for how many gallons at what time in the day, week, month, at which factory, by which supervisor, and stuff like that. So a detailed schedule will be very extensive, but the important question in this example is how many gallons, right? So how many gallons of A? One unknown, one question mark. How many gallons of B? Another question mark, right? So we have two unknowns to think about so that we can set our factory settings for M&D chemicals to produce exactly this number of gallons of A and B so as to achieve the reduction, the minimization of total production cost. So we're going to define two variables. Let's just call them A and B. So then we need to express the total cost. Producing 1 gallon of A takes how much? Oh, it says here, right? $2. Therefore, producing A gallons of A will incur 2A. Producing 1 gallon of B costs $3. Producing B gallons of B will cost us 3B. So therefore, the total production cost will have to be 2A plus 3B. And then we put a min in front. That forms our what objective function, isn't it? Yeah. So to define our decision variables, we need to pay attention to at least two traits: the unit and the duration. So notice that they say for the coming month, right? For the coming month, that means we're going to decide or plan ahead for that whole month, not the whole day, not the whole week, not the hour, but the whole month, right? So the planning horizon stretches for 1 month, and therefore the number is to be interpreted based on a month's production time. And the number is not liters, it's not barrels, it's not lorry trucks, it's gallons. You see how paying attention to the two traits, right, the unit and the duration, come in long way in making the number for the interpretation part very clear, very unambiguous, right? So we have a couple more constraints like uh, major customers order for 125 gallons of A must be met. So A greater than equal to 125. Okay. A and B requires 2 and 1 hours of processing, and we only have 600 hours. So every gallon of A requires 2 hours. So total number of hours for A, 2A. Every gallon of B requires 1 hour. Total number of hours for B, 1B. So 2A plus 1B less than equal to 600. So you see that this is already there and there's a missing part, right? I hope you already detected it, and that has to be in a month, right? Yeah, so just to bring your attention to this by having purposely missing out missing parts to a complete definition of the variables. So we have the variable definition, the objective function, and regular constraints, and finally A and B must be non-negative, and that wraps up the whole model. Okay, now let's quickly flip over to Excel screen so that we can have a look at um, how it looks like in Excel, right? So the formulation is kind of similar, but not exactly the same thing. Most importantly is that we don't find A and B being listed. It's just the numbers here. All these are numbers, right? And we have some product here. We'll go through the complete setup of a model in details in the next session. So here we're just appreciating that the formulas are in this column called left-hand side value, which doesn't exist in the original model. And then there is a right-hand side value, which is a copy and pasted form of the original model. So we stick as much to the original model as possible. But Excel has its own needs so as to be able to solve and find the answers for us. So the answers here will be A has to be 250 gallons, B has to be 100 gallons. Let's do a quick check. A plus B, 350, and that is satisfying the performance requirements of generating 350 gallons in totality. Right? Customer says make at least 125 gallons of A. We are producing 250, so that's performance requirements. Don't use more than 600 hours of production time. We are using up every single hour available. And notice that all three constraints are met, right? So here we get, if producing 1 gallon of A gets $2, and 1 gallon of B getting $3, we are getting $800 of cost. All right, not getting as in the cost. So this is the minimum we can achieve. It's a guarantee. It's a guarantee by linear programming, by mathematics. So long as we don't get our numbers wrong, so long as we didn't miss out or included in extra constraints, basically this number is assured. In other words, any other combination will not result in lower cost, because even if you get it, it will be breaking some of the constraints. Like in this case, we are not following 350 gallons. Okay, so there is no way to reduce the cost further. Anything you do will make the cost increase, or at the most stay at it as it is. You cannot reduce it. So that's why this guarantee is so useful. It comes free of charge from mathematics. It's assured that your your cost cannot go below it. It is already minimized. And that's not just an estimate. It is absolutely accurately, correctly presented to us. Okay. So, and another example is the ironworks. So they manufacture two kinds of products, right? Again, same things, two products, X and Y, let's say. 2 pounds of steel to make product 1, 3 pounds of steel for product 2. So all these are given. And we need to find the optimal production quantities, a bit like schedule as well, right? So they want to know explicitly I wonder how many product one, how many product two to produce. So again, we need to define two decision variables, link in all the coefficients, and then we can formulate this model. So this month's production level of product one and product two. Yeah, so unit count and duration. Substituting into the model, we can get all these. Okay, so this is a simple example of maximization at work. We want to maximize the what is it? The profits, right? Unit profits. They are $100 and $200, and we translate them into maximize 100x1 plus 200x2. Okay, so if we go over to Excel, we will be able to find that the answer works out to be 60 for x1. So make 60 units of x1 and make 626.6667 units of x2. Okay, it's fractional, that's fine. All right, and thereby enjoying a profit of $131,333, and that's guaranteed. You cannot get more profits from this by satisfying these requirements and having this set of profits, unit profits for products one and two. No way, no way, right? So, so if you did translate all the requirements carefully and correctly from the original question here, didn't miss out anything, then basically the optimal solution 60,626.667 will be ideal, will be optimal. And that guarantee is given by mathematics, solid, free of charge. Usually in business, anything that's a guarantee, you have to buy the guarantee, you have to pay a premium for it. Here, it's free of charge. So quite a shame if we don't use it to our advantage, isn't it? Yeah. Okay. So in the next section, we will rerun this ironworks example, but this time I will build from scratch. We'll start off from a blank screen, and I'll show you how we can arrive at the formulation of this result from a blank screen, right? So we'll do that. So stick around and let's meet again in the next session.